In this module, we're going to be looking at the Schrödinger equation. Now, this possibly has you feeling a little bit nervous, but we do need to cover it. It is in the HSC syllabus. In the final topic in the HSC Physics syllabus, Module 8, you need to analyse the contribution of Schrödinger to the current model of the atom. So hopefully we can keep this nice and simple and understandable. I'll be explaining it to you in a bit more detail than you would need to pass on to your students, but it is important that you have a slightly deeper understanding than they do. But hopefully we'll take it at a slow enough pace for you to get a kind of clear picture in your mind about what's going on. Okay, so to start with, we're going to need to look at what a wave function is. So previously, we've written down equations for lots of different types of waves. So we've written down equations for electromagnetic waves, sound waves, and waves going along a string. Now, here we're going to try and write down equations to describe matter waves. So often electrons, but also other particles as well, because we've seen, as de Broglie said, particles can be described as a particle, but also as a wave. So now we're going to come up with a way to write down that wave equation. Now, naturally, this is going to be slightly more complicated for matter waves than for the other types of waves, as matter waves don't just carry energy, they also carry momentum, mass, and often charge. So in order to write down these equations, we actually need to know a little bit about complex numbers. So the rest of this video is going to serve as an introduction to the parts of mathematics about complex numbers that you actually need to know. So we'll start by looking at what complex numbers are, then we're going to look at how to take complex conjugates, and finally we're going to look at the different forms that we can write complex numbers down in. Usually in physics we write our wave functions down as a polar form of the complex numbers. So I'll show you how to do that, and then once we've looked at this mathematics, we'll move on and look at what wave functions actually are in a later video. Okay, so we're going to start with what are complex numbers. Okay, basically complex numbers are numbers that can be written down in the form a plus ib, where a and b are both real numbers. And what's special here is the I. So I squared is equal to minus 1. Or if we want, we can say I is equal to the square root of negative 1. Okay, so I is known as an imaginary number, which is why it has the symbol I. And if you square it, you end up with negative 1. Okay, so now that we know what a complex number is, let's look at how to take a complex conjugate. Okay, so if we have a plus ib and we want to take the complex conjugate of that, all we need to do is change the sign in front of the imaginary part, which is the ib part. So the complex conjugate of a plus ib is a minus ib. Now, there's a couple of ways that people can write down, take the complex conjugate. If you look in maths books, they'll often put a line over the top to mean take the complex conjugate. We tend to not use this in physics because we often use that notation for vectors. So that's not a notation that you will see in this course. It's just I'm presenting it now in case you see it somewhere. How physicists usually do it is with a little star. So if that's a plus ib star, that star up the top right hand corner, asterisk, means take the complex conjugate. So this is equal to a minus ib. So this is the notation that we will be using in the rest of the course. Now, why we want to do this is that if we multiply a number by its complex conjugate, we actually end up with a real number instead of a complex number. So as we'll see later, for wave functions this is useful because it actually, when you multiply a wave function by its complex complex conjugate, it gives you the probability of finding a particle at a certain place, which is something that you can actually measure. So that's why we'll be doing this. But let's just show that the complex conjugate times the number itself is actually real. So let's do A plus IB conjugate times A plus IB, because this is nice practice with complex numbers. So this is equal to A minus IB times A plus IB. Now we just treat these like completely normal numbers and expand our brackets. So we've got A times A, that's A squared, A times IB, so plus AIB, and then minus IB times A minus IBA, and then minus IB times plus IB. So that is, remember that I squared is equal to minus 1. So we've got I squared times minus B squared. So that's going to be plus B squared. And so these two terms are exactly the same magnitude but opposite sign. So they actually end up cancelling each other out, and we end up with A squared plus B squared. So when we multiply any number by its conjugate, we end up with a real number. Okay, so that's how you take a complex conjugate. Okay, and finally we're going to look at polar forms of complex numbers. So often you'll see wave functions written as something like a e to the I k x, for example. So this is a polar form of a complex number. But what we've been looking at so far is a plus IB. So what we want to know is how do we convert between these two forms. Okay, so what this means is we can actually expand this as equal to a cos kx minus plus ai sine kx. So this is often called the KISS form, cos plus I sine theta. And so the a cos kx, that was our a from before, and the ab is equal to a sine kx. So how we take complex conjugates of numbers in this form is psi star, which is something you'll be coming across a lot, is equal to AE. Now we just change the sign in front of the complex number. So we write this as minus I kx. And then if we want to expand this, this is equal to a cos minus kx plus a sine of minus kx. And now this is pretty neat. You'll remember from your trigonomic relationships, hopefully, that the cos of a negative number is just equal to cos of that number, and sine of a negative number is equal to minus sine of that number. So you can try that on your calculator if you've forgotten that, just to check it for yourself. So we can write this as a cos kx, and then this will be minus ia sine kx. So you can see how taking the complex conjugate, once again, we're just changing the number in front of the imaginary term, and we can do that in this notation by writing a negative in front of the exponential. So then we can show our psi star psi even faster, just multiplying a complex conjugate by the complex number itself is equal to a e to the minus I kx times a e to the I kx. And so we've got two a's here, so this is a squared because they're multiplied together, and then we've got e to the minus I kx times e to the I kx, so that's times e to the 0, and anything to the 0 is 1, so this is just equal to a squared, which is how we'll often see our complex conjugates being applied when we're looking at wave functions.